Okay guys, the internal generator of this simplified circuit, which we eliminate the brush voltage drop, and also we already combine the adjustable resistor into field resistor. So it was stated that internal generator of EA is equal to constant V times omega m, speed of the shaft. And another one, we have a induced torque of constant also V times IA. So this is the two component formula that given, or we should follow for DC motor. So if we measure on the shaft, so this is the induced torque, and also if we measure on the motor terminal as well, in the internal, so this will be the internal generated voltage of EA over here. So over here is your VT, meanwhile here is your VF, the voltage of the field terminal, and here are the voltage of your armature terminal. Okay, when we use these two formula, we can see that the internal generated voltage is proportional to the flux, and also to the rotational speed of the motor. Okay. Previously, if we can see that for MMF, and electromagnetic force, is equal to NA times IA, and the number of turns of your armature turns times the amount of current that pass through your IA. So this is the amount of generated magnetomotive force on the field. And so the field current in the DC machine, the field current here, will produce field magnetomotive force MMF using this formula. Sorry, NF times IF, not IA. NF times IF, the current that flows into your field here, will produce MMF to the motor. So if you plot this MMF versus the flux or the phi that produced to the motor, we can see that, so this is your MMF, which is equal to NF times IF. We can see that after you increase to certain field, so if either you increase the number of turn, or if you increase the amount of field current through here up to this stage, even though you increase some more in terms of the current or turns, you cannot push anymore. It means that you cannot increase anymore the flux value. It will stick here, and it means that you are wasting your field current or the number of turns, but you cannot increase more flux into the motor. Okay, another graph is that when we plot the internal generated induced voltage compared with your field current, also you will see the same. After it reaches certain knee point of your value, means that after it reaches certain value, so it will produce no more increment in terms of voltage. So this is the maximum. This is what's called a maximum power point of the magnetization curve of a DC machine. Same goes to here. This is a knee point, the point whereby you are not encouraged to increase in terms of field current or number of turns to your motor, because it will give no more effect to the generated internal voltage or the generated flux to the system. So usually as engineer, you are encouraged to find what are the area of this maximum power point or this maximum knee point, such that you don't have to push anymore or increase anymore or put anymore in terms of investment to your system, such that you increase further your field current or your number of turns, but you get less in terms of increment in EA or your flux. Okay, as a result, you can see that there is a curve of flux versus MMF, and flux, the curve of internal generated EA versus IF. Okay, we go directly to the individual type of DC motors. Okay, first of all is the separately excited DC motor. So actually what you need to do is that you have to recognize between each of schematics for, or you're able to reproduce actually for different kind of type of motors. So how the schematics should be look like. From this schematic you can produce the related interpretation of the formula based on simple KVL and KCL and analysis. So let's say we are looking at this separately excited DC motor. Means that each of your terminal, and this is the simplified VT, simplified circuit of your separately excited DC motor. So we have a V terminal which connected, and we have VF, V to the field circuit and V to the terminal circuit, which comes from different voltage source. Maybe both of the voltage are the same, but for separately excited, so we are separating both. Means that we are able to control maybe in terms of VF, we shall control the speed by reducing the voltage at this field terminal. At the meantime, we will stick, or we will fix the voltage terminal at certain level only. Okay, as for this circuit, you just apply KVL. Let's say you apply to the armature circuit. So VT is equal to V is equal to IR. So VT is equal to I, which cross RA plus EA. Or we can write as standard formula, which is EA plus IA RE. Both are the same. And then what else we have here? So we have IA and IL flowing through the same line. So IL is equal to IA. And then the second loop we have here, VF is equal to I. So here are IF times RF, or we can reshuffle. IF is equal to VF over RF. So you will get the same like here. IF is equal to VF over RF. VT is equal to EA plus IA RA. And I load is equal to IA. So same goes to other kinds of circuit. You can use simple KVL and KCL analysis to reproduce the formula. So you don't have to remember actually, but you have to, you should remember how the circuit looks like, and you are able to produce the related equivalent circuit out of the related equivalent formula out of the circuit. Okay. Okay, let's do the example number 1. Previously, I told you that we shall replace this example number 1 with the available example in the books, but we try to solve this example first, then we continue with the example in the book as our second task. Okay, we have here 30 horsepower of 240 volt terminal voltage and 110 ampere rated. So this is all the rated value. When we mention the characteristic, this usually we have this kind of data or information from the nameplate of the motor. Means that this is the maximum rated the motor can handle or can operate. Same goes to this is the maximum terminal voltage value that the motor should connected to, and this is maximum current at the maximum load, rated load of the motor. So this is the maximum or rated speed of the motor, and this is the internal armature resistance, series resistance of the motor, field resistance, field voltage. Means that we have separately excited DC motor. The terminal voltage is 240, the field voltage is 120. Winding for field circuit 2700 turns per pole. Winding on the series circuit and stator circuit, we have here 30 turns per pole. So all this data, by right, when you have this kind of question, you re-sketch the schematic, put in all the data inside, then we produce the formula which related to the circuit. And we calculate A, what are the rotational speed at no load and full load of the motor, and the speed regulation at full load, and motor speed at another value of RF. Okay, we try to solve and discuss and solve here. So first of all is that you need to do, you draw the schematic of this motor. So just a generic motor schematic of a motor which have RF here, we have L here, so this is your RF, this is your VF, so this is your VT, and this is your EA, positive, negative. Symbols here, positive, negative, positive, negative. So we are putting all the data inside the schematics. So we have armature resistance, this is RA, which is 0.23 ohms. We have series resistance, okay. A series resistance means that your resistance which include all available at the armature side. And series resistance means that the resistance value of the wire itself. After terminal voltage, the resistance of your wires before it goes to your armature resistance is the resistance of your coil and in the stator part. So we have here 0.02. So we have here 0.02 of RS, and we have 0.23 of RE. Then we have our field resistance of 165 ohms, field voltage of 120 volt. So terminal voltage of 240 volt. So you write the number and also with the unit. And so you draw nicely compared to mine.